The early 1960s represented a period of absolute technological fearlessness, where the limits of orbital lift capacity were challenged by the most radical engineering concepts ever put to paper. While NASA was meticulously developing the Saturn V to reach the Moon, a parallel and far more ambitious vision was taking shape at Aerojet, under the leadership of a brilliant and unorthodox engineer named Robert Truax. This was the Sea Dragon, a conceptual two-stage orbital launch vehicle designed to be the largest and most powerful rocket in human history. Standing at a staggering 150 meters tall with a diameter of 23 meters, the Sea Dragon was not designed for a traditional launch pad. Instead, this behemoth was intended to be built in a shipyard, towed into the open ocean, and launched directly from the water. It was the ultimate expression of the big dumb booster philosophy, a strategy that prioritized sheer mass and simplicity over delicate and expensive complexity. The Sea Dragon was designed to place a monumental 550 tons into low Earth orbit in a single launch, a capacity that would have allowed for the construction of entire space stations or Mars expedition vehicles with a single flight. This rocket was not just an evolution of existing technology. It was a maritime giant that promised to make space travel as routine and cost-effective as ocean freight. Before we delve into the mechanical sheer scale of this aquatic titan, please take a moment to hit the like button and subscribe to Never Built. We uncover the lost future that the world canceled. We promise you this: stick with us until the final segment, and you will learn the one specific, terrifying acoustic calculation that proved a Sea Dragon launch would have shattered the eardrums of every living creature within a 20-mile radius of the splashdown zone. Here is why this ultimate symbol of maritime space power was abandoned. The first, overwhelming obstacle was the marine corrosion and buoyancy paradox. To launch from the ocean, the rocket had to survive the highly corrosive saltwater environment while maintaining perfect vertical stability in choppy seas, a feat that required a massive and expensive specialized ballast system. The second, inescapable hurdle was the single-engine catastrophe risk. The Sea Dragon relied on one gargantuan engine with 80 million pounds of thrust, a design so massive that any minor vibration or combustion instability would have resulted in an explosion equivalent to a tactical nuclear weapon. Finally, the project was fatally wounded by the infrastructure displacement. The sheer cost of building the massive shipyard facilities and specialized recovery fleets required for the Sea Dragon would have forced NASA to abandon the Kennedy Space Center entirely, a political and financial sacrifice the agency was unwilling to make. The core engineering philosophy behind the Sea Dragon was a direct rebellion against the miniaturization and complexity of the early space program. Robert Truax argued that the most expensive part of a rocket was its complexity and the precision required for lightweight materials. His solution was the big dumb booster concept, building a rocket out of thick, pressure-fed maritime steel rather than aerospace-grade aluminum. The Sea Dragon's first stage was designed to be as simple as a submarine hull, capable of being welded in a conventional shipyard. This approach promised to reduce the cost per pound to orbit significantly, as the materials were cheap and the tolerances were far more forgiving than those of the Saturn V. However, this massive weight required an engine of unprecedented scale. The single first-stage engine was designed to burn a mixture of liquid oxygen and kerosene, generating more thrust than all the engines of the Saturn V combined. The engineering challenge of cooling such a massive nozzle and preventing pogo oscillations in a thrust chamber of that diameter was a theoretical nightmare that remained unsolved at the time of the project's cancellation. The sheer volume of propellant moving through the system meant that even the slightest deviation in pressure could lead to a catastrophic structural failure, turning the ocean launch site into a scene of industrial devastation. The ocean launch logistics were both the Sea Dragon's greatest innovation and its most complex failure. The rocket was designed to be towed horizontally by a specialized nuclear-powered tugboat to a launch site in the deep ocean. Once on site, a massive ballast tank at the base of the rocket would be flooded, rotating the entire 150-meter structure to a vertical position. The rocket would then sit in the water like a giant buoy, with only the upper stage and payload visible above the waves. This method eliminated the need for a multi-billion-dollar launch tower and pad, which are the most vulnerable parts of a traditional spaceport. However, the reality of saltwater intrusion presented a constant threat. Every valve, sensor, and electrical connection had to be perfectly sealed against the high-pressure marine environment. The risk of a single seal failing during the hours of towing and preparation was immense, and the cost of marinizing a liquid-fueled rocket to this extent threatened to nullify the savings promised by the big dumb booster philosophy. The ocean was not just a launch pad. It was a corrosive and unpredictable adversary that demanded a level of structural hardening that aerospace engineers were not prepared to provide. The environmental and strategic impact of a Sea Dragon launch was another area where the project faced insurmountable opposition. The sheer acoustic energy generated by 80 million pounds of thrust hitting the water would have created a shockwave of staggering proportions. Scientists calculated that the sound would not only be lethal to marine life in the immediate vicinity, but would also create localized tidal waves that could threaten coastal regions and naval vessels. Furthermore, the risk of an abort on the water was a terrifying prospect. If the Sea Dragon suffered a catastrophic engine failure or a structural collapse shortly after ignition, the resulting explosion of millions of gallons of liquid fuel would create an environmental disaster of unprecedented scale in the open ocean. The political fallout from such an event would have likely ended the American space program, making the Sea Dragon a high-stakes gamble that NASA's leadership, already focused on the prestige of the Apollo program, was simply too conservative to take. Finally, the strategic obsolescence of the Sea Dragon became clear as the space race transitioned from raw power to precision. While the Sea Dragon was perfect for hauling massive amounts of bulk materials to orbit, it lacked the finesse and flexibility required for the complex orbital maneuvers and docking procedures that the lunar mission demanded. NASA realized that it was better to have multiple, smaller, and more reliable rockets than one single, massive, and incredibly risky vehicle. The industrial base required to support the Sea Dragon, massive shipyards, heavy lift tugs, and deep water ports, was entirely different from the established aerospace infrastructure of the 1960s. To commit to the Sea Dragon was to abandon the entire ecosystem of aerospace contractors that had been built around the Mercury, Gemini, and Apollo programs. The Sea Dragon was a titan born out of its time, a magnificent engineering vision that was ultimately too large, too loud, and too dangerous for the world it was meant to conquer. The second phase of the Sea Dragon's conceptual evolution centered on the structural paradox of the big dumb booster and the extreme metallurgical demands of a rocket that functioned more like a submarine than a spacecraft. Robert Truax's insistence on using 8mm thick AISI 4130 steel for the hull was a radical departure from the delicate aluminum-lithium alloys used in traditional rocketry. While this made the Sea Dragon incredibly robust and capable of withstanding the immense pressures of being submerged in the ocean, it introduced a catastrophic weight penalty that only the most powerful engine in history could overcome. The engineering team had to solve the problem of pressure-fed simplicity versus structural integrity. Unlike the Saturn V, which used complex high-speed turbopumps to force fuel into the engines, the Sea Dragon was designed to be pressure-fed using liquid nitrogen. This eliminated thousands of moving parts, but required the fuel tanks themselves to be built as massive pressure vessels capable of containing hundreds of pounds per square inch of pressure without rupturing the entire airframe. The manufacturing and assembly logistics of the Sea Dragon were designed to bypass the limitations of traditional aerospace factories. The plan called for the rocket to be built in a large-scale naval shipyard, such as the one in Newport News, Virginia. This allowed the project to utilize existing heavy industrial infrastructure designed for building supercarriers and nuclear submarines. The first and second stages would be constructed as massive cylinders and then welded together on a specialized dry dock facility. However, the sheer size of the welds required for the steel hull presented a massive quality control risk. A single flaw in a weld at the base of the rocket, where the pressure and stress were at their peak during launch, would lead to a catastrophic structural failure. The cost of X-raying and certifying every inch of the Sea Dragon's massive steel frame began to erode the low-cost promise of the big dumb booster philosophy, turning a simple steel tube into a multi-billion-dollar precision instrument that required shipyard workers to perform with the accuracy of watchmakers. The engine combustion dynamics of the single massive first-stage engine represented the project's most significant leap into the unknown. To lift 18 million pounds of steel and fuel out of the water, the Sea Dragon required an engine with 80 million pounds of thrust. The combustion chamber was so large that a small car could be driven through it without touching the sides. The primary engineering fear was acoustic instability within the chamber itself. In large rocket engines, the combustion process can create massive sound waves that bounce off the walls of the chamber. If these waves synchronize with the engine's vibration, they can tear the entire structure apart in milliseconds, a phenomenon known as pogo oscillations. While the F1 engines on the Saturn V struggled with this on a much smaller scale, the Sea Dragon's engine was an order of magnitude larger. There was no test stand on Earth capable of firing such an engine, meaning the first time the world would know if the Sea Dragon worked was during its first actual launch in the middle of the open ocean. Furthermore, the marine buoyancy and ballast control system added a layer of naval architecture that was entirely foreign to NASA's aerospace engineers. To transition the rocket from its horizontal towing position to a vertical launch position, a massive ballast tank at the base of the first stage had to be flooded with seawater. This process had to be meticulously controlled to prevent the rocket from oscillating or capsizing in heavy swells. Once vertical, the rocket's center of gravity had to be perfectly aligned with its center of buoyancy to ensure it did not lean during the critical seconds of ignition. The engine itself was designed to be submerged in saltwater, requiring a massive retractable plug or nozzle cover to prevent the ocean from flooding the combustion chamber before launch. The reliability of this underwater ignition sequence was one of the project's most debated points, as any failure of the nozzle seal or the ignition timing would result in the immediate sinking of the world's most expensive piece of hardware to the bottom of the Atlantic. The logistical nightmare of the recovery fleet also weighed heavily on the project's feasibility. While the Sea Dragon was designed to be partially reusable with the first stage splashing down in the ocean for retrieval, the reality of recovering a 150-meter-tall steel cylinder from the open sea was a task of Herculean proportions. It required a fleet of specialized deep-sea tugs, massive floating cranes, and a mobile dry dock facility that could stay on station for weeks at a time. The cost of maintaining this specialized space navy was a significant addition to the project's operational budget that was often omitted from initial low-cost estimates. Moreover, the damage caused by saltwater corrosion during the splashdown and subsequent towing back to the shipyard meant that the reusability of the first stage was largely theoretical. The cost of cleaning, refurbishing, and recertifying a steel hull that had been dunked in corrosive brine and subjected to the immense stresses of atmospheric re-entry often exceeded the cost of simply building a new one from scratch, ultimately undermining the entire economic foundation of the Sea Dragon program. The third critical phase in the life of the Sea Dragon project involved the acoustic and environmental catastrophe that planners realized would accompany every single launch. While traditional rockets at Cape Kennedy already created sound waves capable of rattling windows miles away, the Sea Dragon was an entirely different class of destructive force. The physics of a single combustion chamber generating 80 million pounds of thrust meant that the low-frequency acoustic energy produced would be equivalent to a continuous localized earthquake. Scientists conducting simulations for Aerojet and NASA found that the water surface, rather than dampening the noise, would act as a massive reflective plate, bouncing the sound waves across the ocean surface for dozens of miles with minimal attenuation. This led to the discovery of the lethal sonic perimeter, a zone extending nearly 20 miles in every direction where the decibel levels would be high enough to cause immediate permanent hearing loss or internal organ damage to any biological life, including whales, dolphins, and crew on nearby support vessels. The sheer energy released at the moment of ignition threatened to turn the surrounding ocean into a boiling cauldron of acoustic pressure, a biological dead zone created in the pursuit of orbital dominance. The oceanic shockwave paradox also presented a major threat to the rocket's own structural integrity during the first seconds of ignition. When the massive engine fired while partially submerged, it would create an instantaneous steam explosion as the heat of the exhaust hit the seawater. This would generate a colossal high-pressure bubble of gas and steam that would violently displace thousands of tons of water. The resulting surge would create a localized tsunami that would buffet the rocket's hull before it even gained enough velocity to clear the water's surface. Engineers worried that these unpredictable hydrodynamic forces could cause the Sea Dragon to tip or oscillate beyond the control limits of its gimbaled nozzle, leading to a structural collapse or a catastrophic tip-over explosion just meters above the waves. The complexity of stabilizing a 150-meter tower against the very forces it was generating became a primary argument against the feasibility of the ocean launch concept. The rocket was effectively fighting against the ocean. It was born from creating a chaotic environment where the boundary between a successful ascent and a massive structural failure was measured in fractions of a second. The strategic and political isolation of the project further accelerated its downfall. By the mid-1960s, NASA had already invested billions of dollars into the moonport at Merritt Island, Florida. The infrastructure for the Saturn V, including the vehicle assembly building, the massive crawler transporters, and the specialized launch pads, was already a reality. Robert Truax's Sea Dragon essentially demanded that NASA abandon this entire ecosystem in favor of a naval-based infrastructure. The project would have required moving the center of American space power from the land-based aerospace industry to the shipyards of the East and Gulf coasts. This created an intense bureaucratic rivalry. The established aerospace contractors who specialized in delicate aluminum structures and complex turbopumps saw the Big Dumb Booster as a direct threat to their business models. They lobbied heavily against the Sea Dragon, arguing that it was a regression into crude technology that lacked the precision and sophistication required for the Apollo era. This political friction meant that the Sea Dragon was never evaluated purely on its technical merits, but was instead treated as a hostile interloper in a multi-billion-dollar industry that had already chosen its path. Furthermore, the liquid hydrogen logistics for the second stage introduced a cryogenic nightmare on the high seas. While the first stage burned simple kerosene and liquid oxygen, the second stage required liquid hydrogen to achieve the necessary efficiency for orbital insertion. Maintaining liquid hydrogen at near absolute zero temperatures, while the rocket was being towed through tropical waters for days, was a task that exceeded the capabilities of 1960s insulation technology. The boil-off rate of the fuel during transit meant that a dedicated cryogenic tanker would have to accompany the Sea Dragon to the launch site, constantly topping off the tanks until the moment of ignition. The risk of a hydrogen leak in the humid, salt-laden air of the ocean was immense, as hydrogen is highly explosive and its flames are invisible in daylight. The total complexity of the marine space logistical chain was beginning to look far more expensive and dangerous than the traditional land-based approach it was meant to replace. The requirement for a floating cryogenic farm alongside a massive rocket in a potentially unstable ocean environment added a layer of systemic risk that the Big Dumb Booster philosophy simply could not justify. The nuclear tugboat dependency also added a layer of geopolitical and safety complexity that the project's initial proposals had downplayed. To tow a fully fueled Sea Dragon weighing millions of pounds to a safe launch site in the deep ocean, the project required a fleet of ultra-powerful nuclear-powered tugs. These vessels would have to be custom-built for the task, adding hundreds of millions of dollars to the infrastructure budget. The prospect of towing a massive, potentially explosive rocket with a nuclear-powered vessel created a double-risk scenario that worried safety inspectors. If a storm or a mechanical failure caused a collision between the tug and the rocket, the resulting disaster could contaminate vast areas of the ocean with both radioactive material and chemical propellants. The insurance and liability costs for such an operation were calculated to be astronomical, further undermining the cheap promise of the big dumb booster philosophy and moving the project further toward the realm of financial absurdity. The Sea Dragon was becoming a logistical titan that required the total mobilization of the nation's naval and nuclear resources, a price far higher than anyone was willing to pay for a rocket that might never even clear the waves. The fourth and final phase of the Sea Dragon history is the legacy of its abandonment and the definitive shift of human spaceflight toward the precision over power doctrine. The decision to cancel the Sea Dragon in the late 1960s was not a rejection of its engineering possibility, but a calculated choice by NASA to protect the established path of the Saturn V and the emerging space shuttle. The Sea Dragon was the final casualty of the Aero-Naval War, a struggle between two entirely different visions of how humanity should reach the stars. Its cancellation meant that for the next half-century, space exploration would remain tethered to expensive land-based launch pads and delicate high-precision vehicles rather than the rugged mass-produced maritime rockets Robert Truax had envisioned. This strategic pivot ensured that access to space would remain a high-cost, low-volume endeavor for decades, preventing the large-scale industrialization of low Earth orbit that the Sea Dragon would have enabled. The industrial and economic aftermath of the project's end saw the big dumb booster philosophy relegated to the fringes of aerospace theory for decades. The shipyard-based construction model, which could have revolutionized the cost of access to space, was never realized in the 20th century. The specialized research into massive pressure-fed engines and maritime rocket stability was filed away in Aerojet's archives, only to be rediscovered much later by the new generation of commercial space entrepreneurs. The failure of the Sea Dragon established a monopoly of thought that rockets must be as light and complex as possible, a doctrine that only began to be challenged with the arrival of stainless steel rockets like SpaceX's Starship. The Sea Dragon was the original ancestor of the modern heavy lift revolution, proving that the idea was right, but the timing was decades too early for the political and industrial landscape of the Cold War. The dream of launching rockets like ships from the sea died in the boardroom, not on the launch site. The acoustic and environmental lessons learned from the Sea Dragon simulations continue to influence deep sea and aerospace safety protocols today. The data on how high decibel sound waves travel through the ocean's surface provided a foundational understanding of the impact of human noise on marine ecosystems. Furthermore, the challenges of marinizing electronics and structures for the Sea Dragon contributed to the development of more robust materials for deep sea oil platforms and maritime defense systems. The project failed to reach orbit, but its legacy of engineering for the most hostile environment on Earth, the intersection of the ocean and the atmosphere, yielded valuable technical data that surpassed its original purpose. The Sea Dragon proved that the ocean is not just a passive launch pad, but a dynamic and aggressive physical force that demands its own unique class of aerospace engineering and environmental stewardship. The strategic reevaluation of orbital capacity that followed the project's end led to a significant scaling back of human ambition in the post-Apollo era. Without the massive lift capacity of the Sea Dragon, plans for large-scale Mars expeditions, giant rotating space stations, and lunar bases were all significantly downsized or canceled entirely. The world settled for the smaller, more manageable capacity of the space shuttle and the Saturn V, which dictated the size and scope of the International Space Station decades later. The Sea Dragon was the only project that offered the brute force necessary for true interplanetary colonization in the 20th century. Its abandonment marked the moment humanity decided to stay in low Earth orbit for the foreseeable future, choosing the safety of the known over the massive high-risk leap into the deep cosmos that the Sea Dragon represented. We traded a maritime empire in the stars for a fragile foothold in the vacuum. The Sea Dragon remains a magnificent, terrifying monument to a future that was deemed too loud and too big to exist. It was a project defeated by the convergence of bureaucratic inertia, environmental fear, and the unyielding laws of acoustics. The decision to stay with land-based rockets was the definitive moment the space program chose the aerospace path over the maritime path. The Sea Dragon was designed to be the king of the rockets, a steel giant born from the waves to conquer the stars, but it was eventually brought down by the weight of its own ambition and the silence of the politicians who feared its roar. It stands as a testament to an era when humans were not afraid to dream of things that could move the world. The final question remains. The Sea Dragon failed because it was too massive and disruptive for the 1960s infrastructure. Today we are seeing a return to massive, simple rockets built from steel. Do you believe that the ocean launch concept is still the ultimate solution for massive orbital lift, or have modern land-based launch sites become so efficient that the Sea Dragon's aquatic dream is dead forever? Join the discussion below and tell us. Would you be willing to risk an environmental disaster in the ocean if it meant humanity could build a city on Mars in a single decade? If you enjoyed this professional deep dive into the abandoned engineering of the Sea Dragon rocket, like this video, and subscribe to the channel for more stories about the incredible projects that were never built.